Section 5.1, Double Integrals over Rectangular Regions. Your homework is problems 13, 21, 35, and 36. Properties of double integrals. The properties of double integrals are very helpful when computing them or otherwise working with them. We list here 6 properties of double integrals. Properties 1 and 2 are referred to as the linearity of integrals. Property 3 is the additivity of integrals, and property 4 is the monotonicity of integrals. And property 5 is used to find the bounds of the integral. Property 6 is used if f of x comma y is a product of two functions, g of x and h of y. These properties are used in evaluating double integrals. So to begin, I left out a large chunk of the beginning of the chapter, and I chose to not focus on that is because it's just developing volumes and double integrals using rectangular regions and Riemann sums, very similar to what you saw in your first calculus course. So I skipped that for the sense of just getting to what we need to do. So in these theorem 5.1, it's listing all these properties of integrals. So if we have two functions, we can add them up, and we can also move out a constant from the integral. We can add two functions assuming there's no overlapping of space. And 4, we're saying that the inequality holds true with integrals. 5 is for bounds, so we'll see an example of that. All right, now let's talk about interrated integrals. The basic idea is that the evaluation becomes easier if we can break a double integral into single integrals by integrating first with respect to one variable and then with respect to the other. The tool we need is called an integrated integral. So for the notation, you can use brackets to show what you're going to do first. So we have the integral from b to a, bracket, open bracket, the integral from d to c of f of x comma y dy, close bracket dx. Means we integrate f of x comma y with respect to y while holding x as a constant. Similarly, the notation, the integral from d to c, open bracket, the integral from b to a of f of x comma y dx, close bracket dy, means we integrate f of x comma y with respect to x while holding y as a constant. The fact that double integrals can split into integrated integrals is expressed in Fubini's theorem. Think of this theorem as an essential tool for evaluating double integrals. So Fubini's theorem, all it's saying is we can evaluate for a double integral, and we can, in a sense, choose which are we going to evaluate first. Keeping in mind that we keep the other variable as a constant. And this image here shows how what we're doing with these double integrals. We're taking the integral of the length and then basically two visions of, or two perspectives of the height. So here we see an image of what it means to do a double integral. Let's do example 1. Use Fubini's theorem to compute the double integral of double integral r of f of x comma y dA, where f of x is equal to x, and your bound is r from 0 to 2 and 1 to 0. Okay, so these are your bounds. We first have your x's and then your y's. Now, what is our function? We have it here, right? It's just x. So we're going to compute a double integral of x. And you can choose, it doesn't matter which you want to work with first. Since we're working with x and we're integrating with x, why don't we start with x? Now you have to make sure you match your integrals with your bounds. So we're starting with x. X has to be the first integral. So our bound is from 2 to 0. And then we have our y, so then we list our y from 1 to 0. Now, when integrating, you can use your brackets, or what I like to do is just focus on what you're working with. Keep in mind you have to bring down the rest of your function, or the rest of your computation. So we're integrating x. The antiderivative of x is 1/2 x squared. And we need to apply those bounds of 1 to 2. All right, so 1/2 times 2 squared minus 1/2 times 0 squared. Well, that's just 0. 2 squared is 4. 4 divided by 2 gives us 2. Okay, now we need to continue this again. Now we integrate from 1 to 0, dy, and we take our response, our answer, which again was a 2. And it can be anything. It's just in this case, it also happened to also be 2. All right, the antiderivative of 2 is 2x. We apply the bounds from 1 to 0. So 2 times 1 minus 2 times 0, we get 0. Our answer is just 2. Next example. Evaluate the double integral of xy minus 3xy squared dA, where r of x comma y such that 0 is less than or equal to x less than or equal to 2, and 1 is less than or equal to y less than or equal to 2. So here we have our bounds again for our x's and our y's. They're presented differently. And here we're given our equation to work with. Now, it doesn't really matter which one you work with first. We see we have our argument in both x's and y's. So it just depends which one you're working with, or which one you decide to work with. In future sections of this chapter, sometimes you might get stuck working with one variable, so we can choose to redo our problem and start with a different variable. But for this first section, these are pretty kind problems. So let's integrate. Let's start with x. For x's, we have 2 and 0. So 2 and 0. For our y's, we have 2 and 1. And our equation is xy minus 3xy squared. And we said we were starting with x's and then lastly our y's. So you work from the inside, then out. So let's start with our x's. Now, if we're working with x's, remember, y is a constant. So think of that as just a number. All right, so the antiderivative of x is 1/2 x squared. And we have to bring along that y. Minus 3 x squared over 2 y squared. Now, if you like to, by use of our theorems above, or from that first page, that said if you have two functions, you can split the double integral. You can have consult that as well. So let me do that, just for the sake of illustrating that part of our theorem. So let's rewrite our integrals. So I have 2 to 1, 2 to 0, x, y, minus 2 to 1, 2 to 0 of 3xy squared dx dy dx dy. And you can do this. For example, I would do this because I would probably make a silly mistake with that negative. So if I can just work it out, it's something that might be worth doing. Okay, so we're taking the derivative with respect to x. The derivative of x, or I'm sorry, the antiderivative of x is 1/2 x squared. We apply that to the 0, so we're working only with our x's. And that y is a constant, so it just sticks around. Minus, let's work with our x's only. The antiderivative of x is x squared times 1/2, so 3/2. The y squared is a constant, so it also sticks around. All right, let's clean this up. So I have 1/2 times 2 squared times y minus 1/2 times 0 squared times y minus 3/2, 2 squared y squared minus 3/2 times 0 squared times y squared. The cool thing about those zeros is they add to make 0 because, well, they multiply to be 0. And then we have 2 squared is 4, 4 divided by 2 is 2, so we have 2y minus 2 squared is 4, divided by 2 is 2, 3 times 2 is 6, 6y squared. All right, so you evaluate for the integral for x, but you still have to work that integral for y. So we still have the outside of those bounds from 2 to 1. Our result, which is 2y, dy minus our bounds of 2 to 1, so that part that we left out, of 6y squared dy. Notice that y wasn't lost. Okay, let's go ahead and integrate. The antiderivative of 2y is y squared. Our bounds is from 2 to 1. Our antiderivative of 6y squared is a y cubed. To get 6, it would just be a 2. So our bounds are from 2 to 1. All right, let's go ahead and evaluate. So we have 2 squared minus 1 squared minus 2 times 2 cubed minus 2 times 1 cubed. So we get 4 minus 1 minus 2 times 8 minus 2. All right, so this gives us 3 minus 16 minus 2. We get 3 minus 14, which is negative 11. So that is our answer. Example 3. Over the region R of x comma y such that x is less than x is less than 3 and 1 is less than y less than 2, we have 2 is less than or equal to x squared plus y squared less than or equal to 13. Find the lower and upper bound for the integral of the double integral r of x squared plus y squared dA. All right, so here it wants us to find the upper and lower bounds. So this will be an example of our theorem of part 5 about finding the bounds. So to find the bounds given an equation that's already bounded, to apply those bounds for the integral, we're going to integrate twice. We're going to integrate for our 2 and integrate for our 3 using the bounds given here, 3 to 1 and 2 to 1. All right, let's go ahead and give this a try. This is a two-part problem. I'll do one and I'll have you the other. So to begin, let's start with our lower of 2. So we're going to integrate that 2 using those bounds of 3 to 1 and 2 to 1. So we've kind of been starting with x's, so let's continue that trend, but you can change at any time. All right, so if we integrate 2, we get 2x. From 3 to 1, we get 2 times 3 minus 2 times 1 minus, so I'm just doing this part for x. 2 times 1. Oh, I'm sorry. I think I'm getting, that was it. I'm getting, got a bit ahead of myself. All right, so we have 6 minus 2, we get 4. Now we integrate from 2 to 1 of 4 dy. If we integrate 4, we get 4y. We apply the bound from 2 to 1. So we have 4 times 2 minus 4 times 1. X minus x, 8 minus 4 gives us 4. All right, so that's our first answer. Now I'll help you try the other one. So now we're going to integrate for our lower, or I guess our upper bound, which is 13. So we're going to do the same thing, same bounds, from 2 to 1, 3 to 1 of the same function, well, not same function, of that same part of our bounds. This time will be 13. Now that 3 to 1 comes from our x's, so we must write x first. That 2 to 1 comes from our y's, so we must do the y second. Give this a try. Your answer, when you're done, should be 26. All right, this is the second part of our answer. Now, our answer, our question, is find a lower and upper bound for the integral. So, according to this, our upper and lower bounds for our integral are, our answer is we have a lower bound of 4. So I have 4 is less than or equal r, integral for r of x squared plus y squared dA, less than or equal to our second answer, 26. So we have found the lower and upper bounds for our integral. Next example, evaluate the integral of e to the y times cosine x dA over the region of r is equal to x comma y such that 0 is less than or equal to x less than or equal to pi over 2 and 0 is less than or equal to y less than or equal to 1. All right, so I'll let you give this one a try, but I'll help you set it up. Okay, so we're trying to find the double integral. Now we're given the bounds for x and the bounds for y. So for y, we have 1 to 0. For x, we have pi over 2 to 0. Our equation is EY cosine x. Our first letters are x. I'm sorry, our first bounds are x and then y. So we write dx dy. Now, according to our sixth rule, if we have two functions being multiplied, we can also split them. So let's take a look at our sixth rule. In the case where f of x comma y can be factored as a product of a function gx of x only and a function of h of y only, then over the region of R equal to x comma y of x bounded from a to b and y bounded from c to d, the double integral can be written. And notice what happens. We take our double integral, and if one is only for x and one is only for y, I can split my double integral and work with my y separately and work with my x's separately. So taking a look at this next example, we see that here we have my y's only, and here we have my x's only. So I can work with them separately. Now recall, this one is your x's and this one is your y's, so that you don't make a silly mistake of confusing your bounds. So we can rewrite it to be, if we write x's first, we have cosine of x dx, and our appropriate bounds are pi over 2 and 0. And then for y, we have a bound of 1 to 0, and we use e to the y because that's our function for y, dy. That's pretty cool, right? That way you don't have to carry around a dud, I guess you can say, or some heavy weight of a constant variable, of a variable that's treated like a constant. Well, we made it this far. Let's just finish it off. The antiderivative of sine is cosine, vice versa. The antiderivative of cosine is sine. We evaluate from pi over 2 to 0. The antiderivative of e to the y is e to the y, with a bound of 1, 0. Okay, so we have sine of pi over 2 minus sine at 0 times e to the first power minus e to the 0 power. All right, let's finish this off. So sine at pi over 2 is 1, sine at 0 is 0, and then e to the first power is just e to the first power. E to the first to 0 power is anything to 0 power, except 0 is 1. So we're left with 1 minus 0 is 1 times e to the first power minus 1. So we're just left with e to the first power minus 1. Applications of double integrals. Double integrals are very useful for finding the area of a region bounded by curves of functions. We describe the situation in more detail in the next section. However, if the region is a rectangular shape, we can find its area by integrating the constant function of 1, f of x, comma y equals 1, over the region R. Example 5. Find the area of the region of R, x, comma y, where 0 is less than or equal to x, less than or equal to 3, and 0 is less than or equal to y, less than or equal to 2. By using a double integral, that is, by integrating 1 over the region R. All right, so we're integrating by 1, right? Now we use our arguments for x and y. So for x, we have 3 to 0. So dx, 3 to 0. For y, we have 2 to 0. And that's it. I think you can do this one. Your answer should be 6 at the end. We have one more definition. The average value of a function of two variables over a region R is 1 over the area of R times the double integral of the function f of x comma y. Okay, that's it for double integrals. Your homework is 4 problems. You can do more. I just didn't want you to do the same type of problem over and over again. It's just practicing some double integrals and evaluating. All right, that's it for this section. Thank you.